$130,000. That's a Lycoming factory reman in 2026 for an engine architecture designed in 1938. But in 1944, Bristol Aircraft already had an engine rated at 3,000 hours between overhauls. Smoother, cooler running, higher compression, fewer hotspots. The sleeve valve was not experimental. They mass-produced 57,000 of them. So why did the greatest aircraft power plant disappear, and why are you still paying for the engine that replaced it? 3,000 hours. That is the overhaul interval stamped in the Bristol Hercules Maintenance Manual, Wartime Issue, Chapter 8. Not a sales claim, but a factory-mandated number enforced by RAF squadron logs and overhaul cards. 3,000 hours between full teardowns in combat conditions, logged and initialed by ground crews who knew every hour meant another risk over the Pacific. The number is not folklore. The RAF maintenance form MY243 states that a 3,000-hour overhaul interval is the standard for all Hercules Mark 7 engines in frontline service. The records survive, overhaul cards from Filton Repair Depot, squadron logs, and the original maintenance manual. Cross-check any of them. 3,000 hours, strip and inspect. Now compare that to the modern Lycoming IO360, the engine that powers most of today's S4-seat general aviation fleet. The official service instruction 1009AR says it plainly. The recommended time between overhauls is 2,000 hours or 12 years, whichever comes first. Even the most optimistic extensions buried in the fine print top out at 2,200 hours. 2,000 hours is the real-world ceiling. And the Federal Aviation Administration Airworthiness Directive AD20260411 quietly reduced that by another 10% for many owners, forcing early overhauls after a run of bushing failures. That is a 1,000-hour delta. Over a 60-year airframe life, the difference is not theoretical. With a Hercules, you would overhaul twice. With an IO360, you are looking at 3, maybe 4, depending on how the airworthiness directives stack up. Each overhaul in $2,026 runs $38,000 to $85,000, invoice after invoice, every 20 years or sooner if the FAA says so. The cost per hour, the labor, the downtime, all are dictated by that time between overhauls figure, 3,000 hours for the engine you cannot buy, 2,000 for the one you have to. The verified numbers tell the story. The durability gap is not a rounding error. It is a 1,000-hour hole in every owner's logbook, and the only reason it exists is the architecture under the cowling. 57,400 engines. That is the official tally from the Ministry of Aircraft Production, Bristol Hercules units built, boxed and shipped between 1939 and 1951. In 1944 alone, the Filton Works stamped serial numbers on 20,017 Hercules engines. That is not a typo or a rounding error. The wartime ledger, still archived in the Rolls-Royce Heritage Trust, lists the monthly output by hand. January, 1,643 units. February, 1,812. By midsummer, the line was pushing out over 1,700 engines every 30 days. At the peak, the factory was machining and finishing 1,000 sleeves and cylinders per day, an industrial rhythm matched only by the likes of Pratt and Whitney's R2800 line or the mass runs of the Merlin 512. This is not the story of a boutique experiment or a prototype that never left the test cell. The Hercules was a mainline production engine, built at a scale that rivals any piston program in aviation history. Every RAF Halifax, Beaufighter, and post-war civilian freighter that needed a new power plant pulled a Hercules from the same parts bins, the same casting lines, the same overhaul depots. The numbers are unambiguous: more than 57,000 built, 20,000 in a single year, with supply chains measured in tons of nickel-chrome alloy and entire railcars of finished sleeves. The myth that the sleeve valve was a rare or fragile oddity does not survive contact with the production records. The British aviation industry did not just prove the concept, they industrialized it. Hercules engines were stacked in crates, shipped to every theater, and burned through more operational hours than most modern general aviation fleets will see in a century. The scale alone buries the notion that sleeve valves were a dead end. The numbers tell the story, the architecture scaled, the factories delivered, and the RAF flew them until the jets took over. The only thing rarer than a Hercules today is an honest accounting of how thoroughly the sleeve valve conquered the production challenge. Harry Ricardo didn't need a marketing department. He had a test bench, a pressure gauge, and a slide rule. In 1927, Ricardo's laboratory notes spelled out what the sleeve valve could do that the poppet never would. The numbers weren't theoretical. They were measured, recorded, and published in the Royal Aeronautical Society's proceedings. Thermal efficiency was up 12% at the same compression ratio. Not a rounding error. A full grade higher just by changing the way the engine breathed and expelled heat. The secret sits inside the cylinder. The sleeve valve, a thin nickel chrome ring, rotates and slides, exposing ports instead of clattering open and shut like a poppet. That movement isn't just for show. It spreads combustion heat across a larger surface, eliminating the hot spots that eat into valve seats and piston crowns. Ricardo's pressure traces showed peak in cylinder temperature dropping by about 200 degrees Celsius compared to a poppet engine at similar power. Lower temperature, lower wear. The sleeve never faces the full brunt of combustion for more than a moment. There is always a fresh surface. That's why Bristol's Hercules could run 3,000 hours in combat service without ridge wear. The sleeve's rotation and porting erased the sharp step that forms at the top of a poppet cylinder bore. No ridge, no ring break, no sudden death at 1,800 hours. The poppet design can't escape that fate. Every teardown tells the same story. Hard carbon ridge, worn ring, scored bore. Compression ratio is where the sleeve valve pulls away for good. Ricardo's test cells pushed 8.5 to 1 on standard 100-octane fuel without detonation. Poppet engines started to knock at 6.5 to 1, sometimes less. Higher compression means more power per stroke, less fuel per horsepower, and a cooler running engine. That is not a theoretical edge. It is a direct reduction in cost per hour, in gallons burned, in dollars spent keeping the airplane in the air instead of the shop. The Hercules' 12% thermal efficiency gain, the absence of ridge wear, and the ability to run higher compression all flow from one choice: sleeve instead of poppet. The numbers prove it. The architecture wasn't just different, it was better. And the only reason you don't see it under the cowl of every general aviation airplane today has nothing to do with metallurgy or physics or even oil chemistry. It is a matter of what the regulators and accountants found cheapest to approve. Casting scrap rate under 5%. That is the number buried in the Bristol foundry logs from 1944 after the centrifugal shell process came online. Before that, sleeve blanks were a machinist's nightmare, up to 30% scrapped for porosity or out of round. The new line spun molten nickel chrome at 2,000 revolutions per minute, forcing every gas bubble outward, delivering sleeves with a tolerance under 0.02 of a millimeter. That is not a laboratory claim. That is 1,000 sleeves a day, boxed and shipped to Filton, each stamped with a batch code and a hardness check. Scrap dropped to 4.8% by the end of 1944. The process made the impossible routine, mass production at a scale, and precision the poppet world never matched. Now, power. The Centaurus, Bristol's final word in sleeve valve design, ran a verified 3,000 horsepower at 2,700 revolutions per minute during war test overboosts. Ministry of Aircraft production records from June 1945 logged the Centaurus 8 holding 2,850 horsepower for 10 minutes. No meltdown, no valve float, no catastrophic ring failure. The Royal Aircraft Establishment's bench reports back this up. Thermal stability at loads that would have torched any poppet engine. No American radial of the era came close. The Pratt & Whitney R2800 with water methanol injection peaked at 2,200 horsepower. The Centaurus sailed past that with nothing but fuel and metallurgy. Continental Motors tried to match it. In 1934, they built a 6-cylinder horizontally opposed sleeve valve prototype, aiming for 800 horsepower and a new American standard. The bench tests ran clean. But the board minutes from July of 1934 tell the real story: program cancelled, not for technical failure, but for cost. Depression-era cash flow could not cover the tooling bill. The prototype was shelved, the patents filed, and the American market defaulted to poppet valves, cheaper to certify, easier to tool, and already blessed by the Federal Aviation Administration's first type certificate office. Sir Peter Masefield flew the Centaurus and called it the smoothest, the quietest of all piston engines. Not a salesman's boast, a test pilot's verdict, earned at full throttle, logged in the flight test reports. But the numbers on the ground, scrap rates, horsepower, proven time between overhauls, tell the same story. The technology was ready. The factories delivered. The only thing missing was the will to push it past the accountants. After the war, the piston engine market didn't just shrink, it imploded. Demand for high-power radials collapsed by more than 70% between 1945 and 1950, as jets took over the skies and airlines swapped out their propliners for turbofans. The numbers are buried in Ministry of Supply reports. By 1950, the global order book for engines above 2,000 horsepower was a fraction of what it had been 6 years earlier. The Hercules, once rolling out at over 1,000 units a month, faced a world where nobody needed a new bomber engine and the commercial market was retooling for turbines. But even if you wanted to bring the sleeve valve back, say for a modern 4-seat airplane, the wall isn't technical. It is financial. FAA type certification for a new piston design, as of 2024, runs $50 to $70 million before a single customer sees a flying prototype. That is not a theoretical figure. The cost comes from full test cell trials, reliability runs, emissions compliance, paperwork, and a regulatory process that runs on hourly rates and engineering sign-offs. Every engine that enters the US general aviation market has to clear that bar, and the bar is set high enough to keep out anything that is not already in the parts catalog. Once you add in the entrenched supply chain, engine mounts, propeller hubs, STC paperwork, mechanic training, and a maintenance ecosystem built for flat engines, the real cost of switching to a sleeve valve is not just the certification fee. It is a wholesale rewrite of every manual, every service course, every parts inventory in the country. The arithmetic is simple: a $50 million barrier upfront and a market that can't justify the risk. That is how the best engine architecture in aviation history ended up locked out, not by metallurgy, not by reliability, but by the price of a stamp and a signature. The numbers tell the story. The wall is real, and it is made of invoices. Every part under the cowling is a contract, sometimes written, more often enforced by habit and paperwork. In the world of general aviation, the real wall is not just certification cost. It is the supply chain, the parts catalog, the training syllabus, and the oil in the can. The lock-in is practical, not theoretical. Start with the supplemental type certificate system. Every engine swap, every upgrade, every airframe change is chained to a supplemental type certificate that lists in legal detail which engine mounts, propeller hubs, and accessories are approved. The paperwork is written in the language of the poppet valve. Try to fit a sleeve valve radial where a Lycoming sat, and you face a stack of compliance forms, not a technical hurdle. Parts tell the same story. The Lycoming and Continental catalogs run hundreds of pages, every gasket, every bearing, every accessory, all standardized, all in stock. Mechanics train on these engines from day one. Every A and P school in the country teaches the flat 4 and flat 6 as the default. The sleeve valve is a footnote if it appears at all. The tools, the jigs, the test stands, even the torque specs, none of them fit a Bristol Hercules. That is not an engineering problem. It is a market built to keep the familiar running and the unfamiliar out. The most revealing detail comes from a 1979 Rolls-Royce internal memo. When Aeroshell 100U, the only oil that could keep a sleeve valve running without metal-to-metal scuffing, was discontinued, A support engineer had to negotiate a special production run just to keep the last RAF Hercules engines alive. One oil, one batch, one engineer standing between a fleet and forced retirement. The supply chain had shrunk to a single point of failure. When the oil ran out, so did the sleeve valve's last chance. That is how quickly operational support can collapse. No parts, no training, no oil, no engine. The lock-in is total, and it is enforced by every invoice and every empty shelf in the supply room. Stack up the invoices. Take a modern Lycoming IO360, the backbone of general aviation, and price out every overhaul you will need over a 60-year airframe life. With a 2,000-hour time between overhauls and the FAA Airworthiness Directive. In 2026, slicing that down for many owners, you are not getting away with fewer than 3 full overhauls, sometimes 4 if you fly more than 100 hours a year or get unlucky with parts. Each visit to the shop, measured in $2,026, has a low end of $38,000 and a high end of $85,000, all in with labor, Airworthiness Directive compliance, and the usual parade of mandatory extras. The average invoice lands in the $55,000 to $65,000 band, and that is before you add propeller work or accessory replacements. Over 60 years, the math is simple. 3 overhauls at $55,000 is $165,000. 4 at $65,000 is $260,000. That is the price band for keeping a single-engine 4-seater in the air. And it is not a theoretical number, it is the cash flow reality for every owner with a Lycoming or Continental logbook. Now run the same numbers with a 3,000-hour time between overhauls, the Hercules standard, not a dream, but a documented figure from wartime ledgers. 2 overhauls, not 3 or 4. Even if the shop rate matched the modern IO360, you are cutting out one entire overhaul cycle. That is $55,000 to $85,000 erased from the lifetime bill. The cost per hour drops by a third. The difference is not hidden in the margins. It is line item arithmetic. Overhaul frequency multiplied by invoice equals owner pain. Every extra teardown, every early airworthiness directive, every 12-year calendar limit adds up. The architecture under the cowling decides the math. The difference between 2 and 3 overhauls is not just an engineering footnote, it is a $70,000 penalty, paid out of pocket, enforced by the time between overhauls stamped in the manual. The verified numbers tell the story. The engine you are allowed to own costs you more, not because it is better, but because the paperwork made it easier to certify. April 11th, 2026. The FAA issues Airworthiness Directive 2026-04-011, mandating a $2,500 bushing kit and 12 hours of shop labor for every Lycoming IO. 360 built before serial number 20,000. No escape clause, no fleet exemption, just a regulatory invoice stapled to every owner's logbook. For some, it is a scheduled shop visit. For others, it is an early teardown, months or even years ahead of plan. The arithmetic is simple. 1 airworthiness directive multiplied by 1,000 engines equals millions in unplanned costs. Not a design flaw, not a manufacturing error, just the inevitable wear path of a poppet valve engine enforced by paperwork and fatigue cracks. This is the real lock-in. Not physics, not metallurgy, but a system that rewards what is already in the catalog and punishes anything different. The Hercules could run 3,000 hours in combat. The IO360 gets pulled at 2,000, or sooner if the airworthiness directives stack up. Every extra teardown, every mandatory kit, every hour of labor, none of it is a technical necessity. It is the price of choosing the engine that was easier to certify, not the one that lasted longer. Roy Fedden knew the numbers. In 1942, the Ministry of Aircraft Production showed him the door. Fired in the middle of the war, his sleeve valve program stalled, his knowledge scattered. The man who delivered the longest-lasting powerplant in RAF history was written out of the story, replaced by committees and cost controllers. The lesson was clear: endurance and engineering take a back seat to what is cheapest to approve and easiest to support. So here is the question that never leaves the invoice. If a 3,000-hour engine existed, why are we still paying for 2,000? The verified numbers tell the story. The smoothest, the quietest, the longest-lasting piston engine in aviation history, and you've never been allowed to own one. Today, you pay 6 figures for a 1930s engine rebuild because the industry banked on certification, not longevity. The verified numbers tell the story. A 3,000-hour sleeve valve, quietly erased, replaced by engines designed for paperwork, not endurance. Metallurgy, economics, and regulation locked in by cost, not by merit. The smoothest, the quietest, the longest-lasting piston engine in aviation history, and you have never been allowed to own one.